Okay, let's say that we know that the mean age of blue-collar workers in the United States is equal to 40. Now, let's say we want to check whether miners, coal miners, average age is less than 40. In other words, whether or more than 40. In other words, whether younger or older workers are in that industry now, whether the younger workers are discouraged from going into that industry. Well, let's see. I don't have the resources to survey every coal miner in the United States. They're in several different states, Pennsylvania, Wyoming. There's coal miners all over the place, right? So let's say I don't have the resources to sample all of those workers. So let's say I go out and I randomly sort. I do a stratified sample. You know, there's a bigger industry in Pennsylvania. I take more people, but I randomly sort 100. I randomly survey 100 coal workers, right? So now that sample then prevents me with a mean. Let's say the mean of that sample is 42. Average age from that sample for coal miners is 42 years old. And let's say that I also found that the standard deviation, the variability of that sample, happened to be 5 years. Okay, so now I say to myself, okay, well, the mean of that sample of 100 people, 100 workers, is 42, and I'm comparing it to the mean of the entire population of blue collar workers. I'm going to call that all blue collar workers, all. Okay, so I got a different number for the mean for our sample than I did for the mean for the entire population. But does that mean that the real true mean for the coal workers is really different than 40? It's really not equal to 40. Well, I took a sample of 100 people, I got 42. So it seems like coal workers on average are older than the rest of the blue collar working population. But I only took one sample. I mean, who knows what would happen the next time? The next time I might have got 38. Next time I might have got 39. Next time I might have got 41. Next time I might have gotten 27. Who knows, right? The idea here is that I need to determine whether this difference, X bar versus mu, that the population I know, whether or not that's different enough for me to say with 95% certainty. In other words, only a 5% chance of being wrong, alpha is equal to 0.05, that these two means are different, not X bar and mu, but mu for the coal workers and mu for all workers. I need to be able to prove that with less than 5% chance of being wrong. So the problem here is that I'll never know what mu for the coal workers is because I'm not going to sample all the coal workers. I'm going to have to rely on this sample and the variability that I discovered from this sample. This is called a single sample t-test or a single sample hypothesis test. Why is it called single sample? Because you only got one sample, right? You're only taking one sample from one population and you're comparing it to a known mean or value from the other population, right? So we know that we have to figure out how many standard errors apart that the mean for coal workers is from the mean for all workers in order to determine what the probability that we would get this extreme a difference between the two of these, right? We need to know how many standard deviations apart they are. Well, actually, we call that the standard deviation refers to the population variability, the people within this group, right? We really want to know how many standard errors apart they are. In other words, if we took samples of this size, how likely would it be that we would get as extreme a value for a sample result as 42? So we're really interested in standard error. So since it's only a single sample test, that standard error is going to be equal to the standard deviation of the sample. Notice I'm substituting, normally would have been sigma over the square root of n. Right? Normally it would have been sigma. I don't know what sigma is because I only sample 100 people from the coal workers. So I'm going to use the standard deviation from the sample, which approximates the population variability, over the square root of the sample size. Okay, so that's going to be 5 over 10, right? 100, square root of 100 is 10. And that's going to be half a year, right? That's our standard error. So how many standard errors apart are these two values? Okay, well, I'm going to calculate that. And the value, the symbol that I used to represent the number of standard errors apart that these two means are is the t-score. Now, if I had a gigantic population, I would use Z, right? But in this case, I don't know. I took a sample of 100. It's a big sample, but I'm not going to rely on that being a really big sample. So I'm going to call this T. So T is equal to, it's equal to the difference between these two, which is X bar minus mu over the standard error. Okay, so that's going to be equal to 42 minus 40 over standard error, and the standard error happens to be 0.5, right? So that's going to be equal to 2 over 0.5 is 4. Okay, so there are 4 standard errors apart, right? So now we have to say to ourselves, but is that enough that with 95% certainty, I can say that these two means, two actual means are different, right? What level of certainty do I really have this at, right? So in order to figure out what level, how big a difference I need between these two means in order for me to say that they're different with 95% certainty, I have to go to the t-table to find out for my particular sample size how big that difference has to be. So I'm going to go open the t-table. And of course, this is going to be 99 degrees of freedom. Not going to be very clear on here, right? Because it only goes 80 and 100. So I'm just going to use 100 for our purposes. And the t-value I need for 95% confidence, in other words, the tail on the left side is 2.5%, tail on the right side 2.5%. In other words, 5% chance I would get this extreme a difference, this number of standard errors apart, that would only occur 5% at a time if my t-score was 1.984. So that t-score, 1.984, that's what we call Tcritical. And Tcritical is going to be different for every different sample size, right? If our sample size had only been 10, we would have less certainty that we could depend on these two means. So to be 95% certain that they're different, we would need a bigger difference between the means. If we take a bigger sample size, we can tolerate a smaller difference because we're more confident because of the larger sample size. So let's say a 10 would be 9 degrees of freedom. They would have to be 2.62 t-scores apart, standard errors apart. Okay, so in our case, okay, Tcritical is 1.984. The t that we calculated for the difference between these two means is 4.0. Since they're further apart than we need them to be, since the t-value we calculated is bigger than the Tcritical from the chart for our sample size, we can say that they're different. Now, how do we say that? Statistics. In statistics, we start off by announcing what our null hypothesis is, right? I did this kind of backwards on purpose, right? Because really what we're trying to show is that these two means are different. These means of these two populations are different. So, but the way we're going to phrase it is we're going to say that the mean for coal workers is equal to the mean for all workers. And the alternative hypothesis is going to be the one that we want to prove is going to be the mean for coal workers, mean age for coal workers is different than the mean for all workers. Okay, so you know, we know what the mean is for all of them, all of the workers, right? We know it's 40. So I could literally just, instead of putting the mean for all, I could have just put the number 40 in here. Everybody okay with that? You know why I can put that number of 40 in there? We know what the mean is for that population. So I don't have to use the symbol for it. I could just use the number if I want. Would you be wrong if you put mu all in there? No, you wouldn't be wrong, right? But it's a little bit neater to put 40 in there for a single sample test. If it's a 2-sample test, then we really can't do that because we really don't know. Just like we don't know the mean, true mean for coworkers, we wouldn't know what if we were working from a sample for all other blue-collar workers, well, then we wouldn't know what the true mean is either. So we'd have to use mu all. But for a single sample t-test, we can do this. Okay, so we then set our level of confidence that we want, the likelihood of making a alpha error or a type 1 error. In other words, rejecting the null hypothesis when it might be true. In other words, when we might get that extreme of difference. We're going to set our alpha for argument's sake at 0.05. Doesn't always have to be that, right? I could have said we wanted 1%, right? Chance of error. I could have made alpha 1%, in which case Tcritical, the calculation would have been exactly the same for T. But Tcritical for 9 degrees of freedom, right, for a sample size of 10, would have been under 99% for alpha equals 1%, and that would have been 3.25. Okay, so happens in this case, we still Tcritical is still exceeded. But let's say that we had said that sample size was only 5, right? 6. So sample size was 6, then we would have needed a Tcritical for alpha equals 5% of 2.5. We exceeded. But for 99% certainty, alpha is equal to 0.01, we would have needed a Tcritical. We would need it to have exceeded 4.032, which we didn't. So we would have failed to reject the null hypothesis under that circumstance. So depending on what you're choosing as alpha and what your sample size is, you can look up your Tcritical. So in this case, we reject our null hypothesis, right? We say, all right, we reject our null hypothesis that the mean age of coworkers is equal to 40, and we accept their alternative that it's different from 40. In this case, it appears to be larger than 40. So what does that tell us? That tells us maybe that, you know, the younger guys are not going to coal mining, or the older coal miners are not retiring as early, and so on and so forth. But there may be some number of other reasons. Okay? So maybe the younger workers are worried about safety and so on and so forth more than the older workers are, so they're willing to take the risk and so on. So at any rate, whatever our conclusions are with regard to why we got this conclusion, this is the math. This is what we do in biostatistics. We evaluate these probabilities so we can draw conclusions about what the numbers tell us about one population versus another population. Then in epidemiology, you figure out, well, why that might be happening, or what you can do to intervene if it's a negative, if you're seeing a negative impact, or what the results of your intervention and your public health spending is in terms of change in worker health or attitude or mental health and so on and so forth. So that's really what we're doing here. Okay, so now this is interesting that in one case we knew what the mean was for the population, so we only had to deal with one sample here, right? That's relatively unusual. Usually you're dealing with 2 samples. Okay, so before we go any further, this class is going to be a little bit more on hands-on. There is a file in the folder. Let me get it back again. There's a file in the folder called air samples single sample.sav. Okay, that's on Blackboard for this session. If you right-click on that and download it to your computer, so it's on your desktop, I'd like you to open that in SPSS. Okay, so I'll give you a few seconds to do that. Okay, because we're going to work on that now. I'm going to have you guys actually solve this. Before we do that, I'm going to actually, while you're getting it downloaded, I'm going to do some descriptive statistics here. I'm going to go to Analyze, just so you can see the process here. I'm going to go to Analyze, Descriptive Statistics, and Descriptives. I'm going to pick that first. And I'm going to say particulate matter. Okay. I'm going to put it into the variables box. Then I'm going to click into Options. And I'm going to say, oh, we want to calculate the mean, the variance, the range, the minimum, maximum, the standard error. Why not standard error also? We'll take a look at that. I'm going to click Continue. I'm going to click OK. Okay, the output window is going to open up. And this output window tells us, let's see, that the mean is equal to, where's the mean? The mean is equal to 36.13 I think it's micrograms per cubic meter, is the micrograms per cubic meter is the measurement that we're looking at here. So that, yeah, micrograms per cubic meter. Okay, so the average amount of particulate in the air in these samples, right, in this sample, which represents, I'm going to say that this sample represents Brooklyn. Brooklyn, somewhere near the shore. Let's say Coney Island. This represents Coney Island and Brooklyn. Okay, and comes to be an average total particulate of 30.1. By the way, the city actually takes measurements like this. They measure mountain cages. Okay, I'm gonna just show you a quick picture if I can find one. Yeah. That thing. They usually chain it to a light post or something, so nobody steals it. This is New York, after all. So steal it even if they don't. It doesn't matter if they know what it is or not. Ambient. Okay, let's see if I got a picture. Okay. It's again. Yeah. Yeah. Okay, hopefully our recording is going okay though. Okay, here you go. This is what it looks like on the left here. But when you see it on the street, it's a cage. Let's see if there's any pictures for it. Show it in the cage. Yeah, I'm not getting the pictures to come up. This is actually what it looks like. Okay, there's a little thing taking a sample. There's a little, probably taking temperature readings, so on and so forth. That's measuring particulates, monoxide, other ozone. Basically about 6 or 7 pollutants. The EPA requires that the city monitor all over the city based on their regulations of national air quality standards. So they measure this, accumulate the information, and report it to the EPA. And there's even probably a map here. Looks like this map might have been like where they were placed on a particular day or something like that. You can probably, if you go there, I don't think they tell you where they put them, because I think that the problem there is they don't want anybody going around tampering. And they do move them around. They spend the days in one spot, a few days, and so on. So this actually happens. So let's say that these are the numbers. Sample size 16, and we found an average particulate level in Brooklyn. It got moved around several different places of 36 micrograms per cubic meter. Right? So we say to ourselves, well, we're interested in knowing whether or not the particulate levels in Brooklyn are lower than the particulate levels of Manhattan. So let's say in Manhattan, in lower Manhattan, they took I don't know, let's say they took thousands of readings over the past year. And the average particulate level that they had over the past year was 39, right? And it wouldn't be unusual for particulate levels in Manhattan to be, lower Manhattan especially, be higher than the rest of the city, because that's where there's the most traffic, most congestion, most buildings with that are burning fossil fuels and so on and so forth. So you'd expect them to be a little bit higher down there, right? So the question now is, given that we know that the rest of that Manhattan is 38, there's enough samples from Manhattan that we're going to say we know the mean there. And it turns, I'm sorry, I said 39. Given that it's 39, how certain can we be that it's different than the level in Brooklyn? Well, Brooklyn, we don't know what mu for Brooklyn is. We only know that the average for our sample of 16 locations over several weeks is equal to 36. So we need to compare our sample mean 36 x bar to our known mean of 39. So how are we going to do that? Okay, so first thing we're going to do is we're going to write out our null and alternative hypothesis. We're always going to start out with that at that point. Okay, so our null hypothesis, right? What's our null hypothesis? The mean for Brooklyn is equal to the mean for Manhattan. And what's our alternative hypothesis? The mean for Brooklyn is not equal to the mean for Manhattan, right? We're always working with means, and we're always starting with an equal sign in the null hypothesis. Sometimes you see an equal than or and greater equal greater than or equal to less than, but the equal sign's always in the null hypothesis. When you see that mixed sign, equal or greater than or equal or less than, that's called a one-sided test. We'll worry about that once we get a little further on. Okay, so now I know that the mean for Manhattan was, what did I say it was? I think I said it was 39, right? So if I wanted to, I could write this as equals 39 or doesn't equal 39, because I know what this happens to be. Most cases I won't know. If I'm taking samples of two groups, I'll have to leave it the way it was. But in this case, single sample test, I can write that in instead. Sometimes that'll be a key for you to know that it's a single sample test. Okay, and what level of certainty do we want here? I'm going to say alpha is equal to 0.05. That's the level of certainty that we want. Okay? We're willing to reject the null hypothesis, right? If there's less than 5% chance you would get this big a difference between, this was 36, I think, between 36 and 39, this big a difference if the null hypothesis is true. If they're really equal, likelihood of getting this big a difference is less than 5%. In which case, in which case, if the likelihood is greater than 5%, we would get that big a difference, then we would fail to reject the null hypothesis, because we want the likelihood of being wrong here and rejecting the hypothesis to be less than 5%. Okay, so let's go ahead and do this. Now you saw that I did this descriptive statistics, right? I'm also going to go in here just to show you it can be done. Analyze descriptive statistics and explore. Okay, I'm going to go one step further. And in that, I'm going to move the same variable, particulate matter, into the dependence box. I'm going to click on statistics. It's going to say, it's also going to calculate a confidence interval for us, right? So we're not going to use that right now, but I'm going to go ahead and calculate it. And you'll notice that when you use explore under descriptive statistics, does all of the things that descriptives did, but it also does a few more. It tells you the 95% confidence interval, tells you the variance, tells you the range, tells you interquartile range. It gives you some idea of how skewed it is. We're not going to worry about these numbers at this point, but it gives you a little bit more information about that variable. So this is nice. You know, we get a little bit more information from this. Okay, but and even gives you a box plot, so we know the minimum value, the maximum value. We know the median value. We see it graphically. Okay, so let's go ahead now and let's go to back to. I'm just going to highlight. You don't have to go back to the data file if you don't want to, but we're going to go to analyze, and we're going to calculate using SPSS whether or not we can reject the null hypothesis. Okay, so you guys do it. Okay, take this and run a Ttest to determine whether or not you can reject the null hypothesis in this case. Okay, and I see a lot of you guys are logged on to watch, so you can watch on the screen. Is anybody watching from home right now? If you're watching from home right now, type into the chat box, so I know that there are people that are logged in off-site. And I also encourage you, if you're at home, to also do the exercise. Okay, as we go on, I'm going to do this more and more because I really want you guys, athletes, they have something called muscle memory, right? They repeat the same motion, the same drill over and over and over again, right? So I want you guys to develop a little bit of muscle memory so that you know how to use SPSS. You know where to go to analyze something. You know where to go to for descriptive statistics. I don't see anybody typing online. I think it's just us. There's no one online at home that's awake. When you think you got it, just wait. Give me a wave. Oh my goodness! I can't believe I'm getting a call down here. I didn't think, normally I don't have signal at all. So, oh, you know what? I switched from AT&T to Verizon. I actually have a Verizon signal down here. I don't know how they accomplished that. You would think that the signal down this deep, you'd be able to fry eggs on it on the sidewalk, right? Okay, did I see any hands waving there? That you've gotten through this analysis? This SPSS, it takes like a millisecond of processing time to do this. I don't mean to embarrass you, but should happen pretty quick, Yeah. Well, no, hang on a second. Now we're comparing the means now. We're doing our hypothesis test now, right? So as a hint, we're going to go to analyze. What are we doing? We're comparing means. And there is a selection there for comparing means. Then you have to decide which of the 5 or 6 options that you have there for the type of hypothesis test that we're doing. Right? Is it paired samples, independent samples? Is it single sample? Is it so on and so forth? Okay, so up at the top, analyze, compare means. What's that? Yep, single sample. It's single sample, right? Think about it. We're only taking one sample. It's not 2 groups, only one sample. Well, we're only sampling the air in Brooklyn, and we're comparing that to a known number. We didn't take a sample of Manhattan. Right? There's no list of numbers for Manhattan. So that's going to be single sample because it's only one sample that's been taken. And we're comparing to a known value. Okay? So how many of you have the T table up in front of you now? Okay, good. Okay, we're getting there. Right, the rest of you guys. See the T table yet? Okay, we're getting some more. How about on the other side there? Okay, good. What's that? Oh, well, SPSS is not going to make us do that. Okay, but if it's in between 2 numbers, then you would estimate, like if it's 85, you would either choose just 80 or something, the next more conservative, the next lower sample size. Okay, so I'm gonna do this up here. Okay, so if you're looking at your screen, okay, I'm gonna go to analyze. I'm gonna go into SPSS. I'm gonna go to analyze, compare means. Now this is a 1 sample t-test. It's a single sample that we took. We're comparing it to a known value. I'm gonna click on that. I'm gonna move the particulate matter variable into the test variable. And then I'm going to say, well, where am I going to tell it what the value is for mu? The value, the known value for the particulate level in Manhattan. I put it in here. I put it in here I'm going to put 39 in there. So it's going to compare the mean for the sample that we took, X bar for the sample we took, to the value 39, the value for the mean for all of Manhattan, right? The true mean for all of Manhattan. So when I click OK, it's going to actually go ahead and do this t-test. So I'll click OK. The output window pops back up, and it repeats some of the descriptive statistics. It says our sample size is 16, our mean was 36 micrograms, our standard deviation, our standard errors here, and then it calculates a t-score. So I'm going to go down to the second table, 1 sample t-test, and our t-value is negative 1.134, right? So that's the number of standard errors apart that these values are. Now, the degrees of freedom is 15. Now, let's say that that's all it gave me. Let's say that that's the only thing SPSS told me. Does it look like you've, based on what you know about degrees of freedom and the t-score, does it look like this value exceeds critical value of t for 15 degrees of freedom? What do you think? 1.1, is that a big enough t-score to exceed the critical value from the t-table? Well, there's nothing on the t-table that's less than 1.96, right? So there's no way in the world that this is big enough to reject the null hypothesis. If I actually wanted to go and look for what the critical value of t would have to be, I could go to the t-table. I'm going to have to open up the folder again. Okay. I could go to the t-table and look up for six sample size 16, 15 degrees of freedom. I would need a t-score of 2.131. That's my critical value of t. So if I go back to my result from SPSS, have I exceeded my critical value of t? The sign, no, I haven't. The sign doesn't mean anything. You don't have to worry about the sign. The sign, it's really the magnitude. The sign just tells you which one is larger, which one is smaller. In this case, we said x bar minus mu over the standard error. X bar was 36, mu was 39, so it turned out to be a negative number, 36 minus 39, right? But the magnitude tells you whether or not they're far enough apart to reject your null hypothesis with 5% chance of being wrong. So now let's move over on this chart. The next thing you see here is something called the significance two-sided. That's the probability that you would get this big a difference, 1.1 standard errors apart, this big a difference if the null hypothesis were true. Okay, how likely is that the null hypothesis would still be true if you got that big a difference? Well, look, it's 27% chance that the null hypothesis would be true. That, in other words, that's kind of what the probability would be that you'd be wrong if you rejected the null hypothesis. So what has SPSS done for you here? It's calculated the t-value for you. It's displayed the degrees of freedom, and it's told you the chances that you'd be wrong if you reject the null hypothesis is 27.4%. Since you decided you're only going to tolerate 5% chance of being wrong, basically this tells you you're going to fail to reject the null hypothesis. Does that mean that the levels of particulate in Manhattan, Brooklyn are the same, that the null hypothesis is true? No, it doesn't. They could be different. They're just not different enough for us to prove it with a sample size of 16. Okay, so we never say we accept the null hypothesis because we have no, that's not what this is geared to do. We either say we accept we either say we fail to reject the null hypothesis, or we say we reject the null hypothesis and accept the alternative hypothesis. That goes together. When you reject the null hypothesis, you always accept the alternative hypothesis. It goes together like love and marriage. Anybody, you guys know that song? Good. I'm glad there's some reference that I can give in here. And I'm not so old that nobody has any idea what I'm talking about. Okay, so that's pretty simple, right? It's not that complicated, I hope. Right? Yes. I made it up. In other words, it's a known value. In other words, that somebody did all of Manhattan for a whole year and they came up with 39, and we're saying that's so reliable that we're saying we know the true mean in Manhattan, but we don't have the resources to test Brooklyn, right? We don't. You know how it is. City Hall, they test. They worry about Manhattan. They don't worry about Brooklyn and Queens and Staten Island. Certainly don't worry about the Bronx. Right? So they didn't have the resources to test those other boroughs, but they were able to test all of Manhattan and get the true mean particulate level for Manhattan was 39. So I made that number up. If I admit, watch what happens now if I make up the number. Let me think for a second here. 2.35. Let's say I say in Manhattan it's 42. I use 42 instead. Analyze. Now our null hypothesis, the mean for Brooklyn is equal to 42, or our mean for Brooklyn is not equal to 42. Right. So I'm going to go into analyze, compare means, one sample t-test, except this time I'm going to compare my result for particulate level mean to 42. And let's see what happens now. And now I do the test, and the t-score now is 2.318. And the probability of being wrong if I reject the null hypothesis is 0.035, only 3.5%, less than our 5% threshold. Critical time, we reject the null hypothesis and we accept the alternative hypothesis. Could we be wrong? Is it possible that the null hypothesis is still true, right? Well, yeah, it could be. There's a 3.5% chance that they're not far enough apart for us to be able to say this, right? So, but if we wanted to be more certain, we'd have to get a bigger and bigger and bigger and bigger sample size, right? And we may not have the resources for it. So as a practical matter, generally, most studies use an alpha, an acceptable level of error of 5%, or a type 1 error of 5%. Right? Not always, sometimes be 99%. It's something really critical. You might make it 99%, or alpha is equal to 1% chance of having that big a difference. So it forces you to have a bigger sample size. Next week, I'm going to introduce the idea of calculating what sample size you need, power and sample size, so that you can figure out how big a sample that you need before you do a study. And how do you do that? I mean, let's conceptualize that for a second. How would you know how big a sample that you would need in this situation to decide that this sample size is good enough for us to have a good shot at rejecting the null hypothesis? Okay. Well, the way you would do that is you would look at the mean for Manhattan that you know, which is 42. And then you say to yourself, what do I think the mean for Brooklyn is? Maybe I took 1 or 2 readings and I got 35. You say to yourself, well, if the mean for Brooklyn is 35, and the mean for, and I know Manhattan is, I think it's 35, but I know the one for Manhattan is 42. How big a sample size would I need to demonstrate that? We have formulas for you to use that help you calculate that in order to be 90% certain that if you're right about how different they are, you're 90% certain that you'll detect that difference, you'll be able to reject the null hypothesis, then you would need this particular sample size, right? And if you want to be 80% positive that it's going to work, then you would need this smaller sample size, and so on. So you would make that judgment. That's called power. That's the probability of failing to reject the null hypothesis when you should have rejected it. Okay, that's the power. Okay, so 5%, in this case, was the alpha, and our beta, or our type 2 error, we probably would want a sample size that would give us less than a 10% chance of failing to reject when it really should be rejected. In other words, we want that big a sample size, and that chance, 10% failing to reject, tells you that the power of that is 90%. 90% likely at that sample size of detecting that difference. Okay, so that's a single sample t-test. Is that going to happen very much? No, because usually you're comparing 2 groups, right? So now, how do we do that? Right. Okay. So we've kind of gone through this before, right? This is not our first rodeo here. We've tried this before. Okay. But I'm gonna open up some data so that we can see what we would need to do in order to accomplish that. And I'm gonna do this one. I'm sorry. I'm gonna put a new test. Let's see if I got. Let me see what we got here. I think I'm gonna work with this one. Yes, I'm going to open up a file called heart rate Excel file copy. I don't know why it says copy, but it is copy. Oh, actually, you could use either one. There's 2. I don't know what you have on yours. I have 2 on my folder on my desktop. Right? Could use it. It's heart rate Excel file. It's an Excel file. Okay, it's a funny format, right? I have it up there behind me. And the reason for the funny format will come up in just a little bit. We're not going to worry about it right now. Okay, make it a little bit bigger. Okay, here's our sample. Okay, and so in our sample, 1 represents athletes, and 2 represents scholars. I go to University of which is the university that's in. There's always some university that's in trouble, right? It was Pennsylvania for a while. It was so on and so forth. What's the one with the Nazi salute that was just going on? Anybody remember what university that was? Was it Wisconsin? Am I right? Wisconsin? Oh, it was a high school in Wisconsin. Okay, let's say we go to that school. I picked them out because why not? Why not bury them in more misery? We go to that school, and we want to do an analysis of whether the resting heart rate of athletes is different from the resting heart rate of high school scholars. Right? Got a pretty good idea the chances are the athletes going to have lower heart rate, resting heart rate, but we want to test that theory, right? So before we do anything else, we get a piece of paper and we start with our null and alternative hypothesis. Okay. And let's see, mu is equal to mu, and mu is not equal to mu. Pretty consistent start, right? H null and H alternative. Now, what mu's are we talking about here? The mean heart rate for athletes is equal to the mean heart rate for scholars. Or the alternative hypothesis is that the mean heart rate for athletes is not equal to the mean heart rate for scholars. Am I making any prejudgment about which one's bigger and which one's smaller? No. This is what's called a two-sided test. I'm not making any prejudgment about whether or not it's more likely that the athletes have lower heart rates or the resting heart rates, or the scholars have resting heart rates. Who knows? Maybe the athletes have high resting heart rates because they're worried about math tests all the time, right? Because they got to stay on the team, they got to keep it be average, so they're constantly worried. So they have a higher heart rate than scholars. I don't think that's going to be likely, but let's throw a little doubt into this, so at least we can have a little fun with it, right? So that's our null and alternative hypothesis. So what level of certainty do we want to accept here? So I'm going to say alpha is equal to 0.05. Okay, that's what we want to accomplish. That level of certainty, or that we want to be less than that chance of being wrong if we reject the null hypothesis. Okay, this is an important study. If we get it wrong, then we're going to be giving all the athletes in the United States blood pressure medication or beta blockers, right? So we don't want to be wrong about this, right? In fact, maybe we want to make a 1%. Yes.
Do you always choose alpha to be 0.05?
No, that depends on what level of certainty you want. If you could say 10%, 10% is easier to prove, right? Because the Tcritical is going to be a smaller number, so it's easier to reject the null hypothesis. And if you want to be really certain, if it's a very critical situation, it's going to cost $1 bazillion in public health costs. It's going to make a major change in the way that people use the medication or something like that, like aspirin, right? And all of a sudden, we're going to go out and we're going to tell 10% of the population you should be taking aspirin every day, which they do, right? Okay, then you want to make sure that study's right? So you might say, well, we're going to make alpha 1%, make it harder to prove. So that means you need a bigger sample size. Right? Doesn't mean you can't prove it. Just means you need a bigger sample size to prove it if you do that. But often, it'll be 5%. And the other thing you should know about this is that if it comes up 2%, or it comes up 8%, or if it comes up 5.5%, or if it comes up 0.51%, that 0.51%, or 5.1%, that doesn't mean that they throw the idea out. I mean, this is it's just like it's a judgment call. It's like 55 miles an hour is the speed limit on the road, right? Now, does that mean everybody's driving 55? In fact, nobody's driving 55, right? They're all going faster, or they're going slower. They're either in the right lane with the blinker on, going slower, or they're in the middle lane, the left lane, I should say, with the going 40 miles an hour, or they're going faster than 55, right? It's kind of a guidepost, right? They can say, for instance, we know that there's a public health consequence to making the speed limit 65. How do we know that? because the reason why it went to 55, most roads it was 60, 65, even 70 in the United States. They went to 55, they called it the double nickel back in those days. In the early 70s, when we had an oil crisis, we couldn't get enough gas in cars. They were rationing, literally rationing gasoline in cars. You can only gas up on odds and even days based on your last digit and your license plate and so on. What they did was, in order to reduce the lines at gas stations and to conserve gasoline, they made all the highways in the United States a national limit of 55 miles an hour. Well, if you're out in Wyoming, you don't like that, because Wyoming, you'll die before you get to the grocery store, in Wyoming, if you're only going 55, right? So, but they made a national limit of 55 temporarily. I think it only lasted a year in most states until the oil supply was basically back to normal. So what happened? We discovered that the number of highway deaths went down dramatically when they lowered the speed limit, right? So we know it has an impact. So same thing here. If we're going to take this guide post of 5%, if it's something really critical, we might say that if we got to 5%, or if we got to 5.5%, we might, 0.055, we might say, yeah, I don't feel comfortable with this. Maybe we should do a larger sample, right? On the other hand, if it's not so critical, and you got like a little bit above 5%, you might say, let's publish anyway. So this is really kind of a guideline, right? Not a law, it's just a guideline. Okay, so for us, it's a law, because when I ask you on a test sheet, you're rejecting a hypothesis, I'm asking you to make a judgment compared to 5%, right? So for us, it's a law, but really in practice, it's a guideline. So you'll see plenty of studies where, let's say, we found that children in this group had a lower blood lead level, and so on the average, and so on and so forth. Our p-value, the probability of being wrong, is 0.065, 6.5%. Well, what do you mean? You're talking about you didn't get to 5%. Well, yeah, they got close enough to say that they had a lot of confidence that, chances are that we're right, that, these guys have a lower blood lead level than this other group. Okay, so that's basically what we're doing here. So now we want to go ahead and prove this. So how do we go ahead and prove this? Well, we have to figure out, number one, we have to figure out what's the difference between these two means, mu1 minus mu2. How different are those two means? Well, I don't know what mu1 and mu2 are, so I'm forced to use the samples means for those two, right? mu1 and mu2. And we want to know how many standard errors apart. And if normally that would be sigma over the square root of n. We don't know sigma, so we have to use standard deviation over the square root of the sample size. Well, see, we're already getting a little complicated here, because, well, you got a standard deviation for group 1, and you got a standard deviation for group 2. Which one of them do you use? Right? Are they the same? Are they different? What about the sample size? You got a sample size for this and a sample size for this. They might not even be equal. So what sample size do you use? Well, we're gonna learn a bunch of rules on how to do this test, calculate this t-value that we need to know whether or not we can reject the null hypothesis. We're going to learn a bunch of rules, a few rules about how to resolve this equation when you're dealing with two samples, sample 1 and sample 2, athletes and scholars. Okay, so I'm going to do that first in Excel. First thing I'm going to do is that I'm going to edit this a little bit. I'm going to put over here, I'm going to put athletes. Did I spell that right? Athletes. All the ones are athletes, and 2 are scholars. Oops. Okay, so I'm going to find X bar for athletes. I'm going to find X bar for scholars. Okay, so what is X bar for athletes? It's equal to the average for these athletes. And what is it for, oops, parentheses, there we go. What did I do now? Let's try this again. Equals the average, parentheses, for athletes. And this represents the average for scholars. Okay, so now I say to myself, oh, wow, there's a difference between these two, right? Remember X bar A minus X bar S, the two means, we're going to say, that's a pretty big difference. But is it enough with such small sample sizes? Is it enough for me to reject the null hypothesis? Well, now I got to calculate my standard error to see if it's going to be big enough, right? Because remember, my formula for T is going to be equal to X bar 1, X bar for athletes, minus X bar for scholars, over, and I'm going to put this in the parentheses just to keep things neat, right? Make sure it does the calculation correctly. If I were to copy it somewhere, or just if you look at it later, over the standard error. So now, oops, let me put a dot in front of there. Okay, so now you've got X bar A and X bar S. You've already calculated that. But now, in order to figure this out, we need to know what the standard error is. What is the standard error equal to? Right? Well, how are we going to calculate the standard error? Well, we've got another document here. And that document is, where is it? T-test variations. I've updated this, by the way. You'll notice it's 1111. Okay. So here's instructions on how to do the t-test using Excel for a single sample test. Right? Get T is equal to X bar minus mu, whatever mu is, divided by standard error. How do you calculate standard error? It's equal to standard deviation of the square root of n, and then sample size, and so on and so forth. Calculate degrees of freedom for Tcritical. N minus 1 is degrees of freedom. Look up Tcritical for that sample size of T table, compare them. So basically, it's an instruction set for what we just did before. So now, look at this next one. Compare the means of two populations using hypothesis testing. When neither mean is known, you got two samples. You don't know the mean, and both populations are sampled. Okay, this is called an independent or two-sample t-test. This version is where the sample standard deviations are assumed to be equal. Remember, there's two variabilities now. You got a variability for athletes, you got a variability for scholars. It's different. Might be the numbers for scholars might be, like scattered all over the place, and athletes might be very close together. So we don't know that yet, right? So what do? State null and alternative hypothesis. State your level of confidence. What's alpha? Now calculate your standard error. How do you calculate your standard error? Well, now, if we have two groups, right? Well, let's calculate the standard deviation of each of those two groups so we know what we're working with. Okay, so I'm going to calculate the standard deviation for group A, and the standard deviation for the scholars. Okay, what is the standard deviation for athletes? Equal to standard deviation, parentheses, and I'm going to pick up the numbers for athletes. Comes out to be 5.16. And I'm going to do the same thing for scholars. Equals scholars, up to standard deviation, parentheses. I'm going to do the same thing for scholars. And that comes out to be 6.5. Now, what do you think? Can I assume that the standard deviations of these two populations is the same? They're pretty close together, right? As a general rule, right? In other words, nobody's going to shoot you if you don't obey this general rule. But as a general rule, if one is not twice what the other one is, we assume the standard deviations of the two groups to be equal. So in other words, this sample came out to be a standard deviation of 5. This one came out to standard deviation of 6.5. One is not double the other. So we're going to assume equal variances, equal standard deviations. Okay. So if that's the case, we're going to stick with the instructions on this page for assuming standard deviations to be equal. If that weren't true, if one of them were 5 and the other were 12, then we would assume that the standard sample standard deviations are not assumed to be equal, we would have used different formulas there. We're not going to worry about that right now. We're going to stick with what we've been working with right here. So now I got a standard deviation for each one of these things. So now, if I assume these two populations to have the same standard deviation, I can take advantage of pooling these two groups together to get a single standard deviation, which is more accurate because it's 12 people instead of 6 people, right? If I put them together, I get a more accurate idea of what the variability is, assuming that the variances are equal. Well, there's a problem with that. The biggest problem with that is that the sample sizes could be different. In this case, the sample sizes are the same. But in a lot of cases, the sample sizes could be different, right? So we need to do something to get a weighted average of these standard deviations, okay? So what we do is we take this, we pull the standard deviations, calculate something called standard deviation pooled or S pooled. How do we do that? Okay, now, hang up your hats. The square root of the sample size 1 minus 1, in other words, in our case, it would be 6 minus 1, this would be 5, times the standard deviation for group 1, the athletes, squared. That was 5 times 5 is about 25. So it would be 5 times 25 and so on. And then sample size 2, 5, which is 6, minus 1 is 5. Then standard deviation in the other group, which is 6, say 36 squared. And when you square it, times 5 is 30 and so whatever that comes out to, divided by n1 plus n2 minus 2. That gives us a number called a pooled standard deviation. So I'm going to calculate that.
When do you say use this again?
What's that?
When do you use this?
We're using this to calculate the standard error. Okay? Because we need to get it from the standard deviation like we did before. Remember before it was sigma over the square root of n? But we got two groups here. So I have to put them together to figure out what I'm going to use for S. So I'm going to do that right here. Okay? So let's see, what was that equal to again? I'm going to do it in different little cubbies, right? First, I'm going to say equals, I'm going to say sample size n minus 1, right, for athletes. N minus 1 is 6 minus 5, it's going to be 5, times the standard deviation for A, for athletes squared, which would be that number times itself, and hit enter. So that's that first number. Then I'm going to do the second number. I'm going to do this part over here, n2 minus 1 times S2 squared. So that's going to be equal to, going to be sample size for scholars is 6 minus 1 is 5 times the standard deviation for scholars squared. In other words, times itself. And that comes out to be that number. Well, the top part of this fraction is just the two of those added together, plus. So I'm going to say that's equal to the sum. It's equal to, I'll just do it this way, equal to this plus this. And adds, that's the top of that. Top of that equation is 344, right? I'm not doing anything really exotic here. I'm just filling these numbers into the equation, right? And on the bottom is going to be n2, n1 plus n2, that's 6 and 6 is 12. 12 minus 2 is going to be 10. So on the bottom of that equation, we're going to put 10. So now let's actually calculate this. Okay, it's going to be equal to, in other words, this value, the standard deviation pooled, is going to be equal to 346 divided by 10. Well, wait a second. I got to take the square root of that also. So I'm going to do it all in one shot. I can either do that, or I can then go over here and say equals square root, parentheses, of this number. And it comes out to be 5.87. Notice our pooled standard deviation, right? This is going to be, I'm going to put that over here so we can see where it is. Our pooled standard deviation winds up being a number between the two standard deviations of these populations. Okay? Now, you can't just say equals standard deviation, parentheses, and then take all these numbers. Okay, I got a different number. Did I do that right? I think I did that right. Because you have the lowest one and one, there's a lot of reasons why you can't just do that, right? Not the least of which is that the sample sizes could be different. So if the sample size for athletes is larger than this number, instead of being kind of weighted in the middle, it's going to be closer to athletes than this, and so on. So that's why we do that. We calculate pooled standard deviation. But we're not yet done yet, right? Our actual value that we need to calculate is t. And how do we calculate t? T is equal to x bar 1 minus x bar 2. I'll put it in parentheses just to be consistent, divided by the standard error. Well, what is the formula we use in this case? Well, it's x bar 1 minus x bar 2 over the standard error. But the standard error is not the pooled standard deviation. That's just the pooled standard deviation. We haven't actually calculated the pooled standard. Normally if there was only a single sample, it would have been the pooled standard deviation divided by the square root of the sample size. But the sample sizes could be different. We got another problem, right? So instead, it's the pooled standard deviation. It's pooled standard deviation times the square root of 1 over each sample size. The square root times pooled standard deviation times the square root of 1 over n1 plus 1 over n2. This is a pain in the butt, isn't it? That's why over time you're going to grow to love SPSS, right? Because it avoids having to do all of this. Let me do this. Let me actually do the calculation now. Okay, I'm going to start with finding this value. First of all, number 1. I'm going to start with the top number. The top number is the difference between the two means. That's equal to 64 minus 71. That's our top number. The bottom number is minus 7. So the bottom number is going to be, well, first I need my pooled standard deviation for the bottom number. And that is equal to, where to go? It's 34. 5. Whoops, I didn't put equals on. Equals that. Okay, and that I'm going to multiply by the square root of 1 over, sample size is 6 rather, 1 over 6 plus 1 over 6. Okay, I'm going to calculate that over here. It's equal to, okay, and first I'm going to do the inside there. Okay, I'm going to say it's equal to 1 over 6, 1 over 6, added to 1 over 6. Okay. And what I'm going to do is, rather than just stop there, I'm going to put that into parentheses and say, if you take the square root of that result. I'm going to leave it there. Leave it right there. And that comes out to that number. Okay, so that number is going to be the number that we multiply SP's pooled standard deviation. We're going to multiply it by the square root of 1 over n plus. We're going to multiply by that number. I'm going to put this over here. And the bottom of our equation then becomes these two numbers multiplied together. Now, I'm doing this stepwise rather than building into a single formula, just so you can see how I'm building on the calculation. So now, in order to find my t-score, what is my t-score? It's equal to x bar 1 minus x bar 2. That's 97, right? Over, I should have put a over in there. Over, divided by this pooled standard deviation times the square root of 1 over n1 plus 1 over n2. Okay. I should have had a parentheses in there too. Just want to be as correct as possible with this. Okay. Okay, and that's what I calculated here. So my t-score is equal to, what is it equal to? It's equal to the numerator divided by the results of the denominator. Our t-score is minus 1.9664. Okay, what's our critical value of t? Okay, how do I find my critical value of t? I go to my t-table, right? Okay, so I'm going to go to my t-table. Okay, there's my t-table. Critical value of t for my t-table is, and we're coming to the conclusion here, right? The critical value for t is, well, what degrees of freedom do I use? What's our sample size? Well, we got sample. Well, no, that's two samples, size 12. So can I use n? What am I going to do? Do I have instructions? Well, wait a second. If you look in the instructions here, degrees of freedom is equal to n1 plus n2 minus 2. So it's going to be 10. So I use my critical value of t. I use 2.228. Okay. So I'm going to go back here. Did my value of t exceed my t critical, which was equal to 2.228? Does it exceed it? No, it doesn't. Can I reject the null hypothesis? Can I reject the null hypothesis? Is my t value bigger than my t critical? Don't worry about the negative sign, just absolute value. Is it larger value than my t critical? No, it's not. So what happens with the null hypothesis? We fail to reject the null hypothesis. The two means are not far enough apart for me to reject the null hypothesis. This was a lot of work, right? Okay, let's do this. Now you guys do the same thing in SPSS. Do a t-test in SPSS, except this time it's not a single sample t-test. It's a independent samples or two sample t-test. Okay, and you have a version of this file. It's called heart rate independent sample .sav. Okay, so open that up in SPSS, and let's see if we get a similar result. I sure hope we do. That was a lot of work. I need to go back over that, try and figure out where we went wrong. But you get why people create software, vertical software, like SPSS, to solve these things for us. Now notice I've coded this for you. I've told SPSS that one represents athletes and two represents scholars. You can see that if I turn the view values on and off, you'll see ones and twos over there. That's important because you're going to run into a little bit of an issue there when you do your independent samples t-test, because it's going to ask you for what the values are. It's not going to. You're not going to be able to put in athletes, scholar. You have to put in the actual thing that represents athletes, scholars. In this case, 1 and 2. They're going to give you a couple of minutes to do that, and then we're going to take a break, which you richly deserve after this. And as a hint, analyze, compare means, independent samples t-test. Now, the little twist that we have here now is that you're going to put into the dependence box, you're going to put the thing that you're going to be finding the average of. In other words, the heart rate. And then to split it up into two groups, you're going to put the nominal variable, the sample, athletes versus scholars, the sample variable, into the factor box. And then tell it that you're factoring it by athletes and scholars. In other words, 1 and 2. Going to pop up a little box there asking you to define the groups. Okay. The thing you're finding the average of, the actual calculation for the averages, that's your dependent sample. It goes into that's your heart rate. And then you're going to factor it or break it up into two groups. In other words, athletes and scholars. I could have given it a bit of a name, I guess, then. Sample. I think I started that because originally I had sample 1 and sample 2 before I made up some sort of weird backstory for the actual calculation. You guys give me an idea when any of you guys get that T table up. Actually, you're looking at the T table as a result of this. Throw your arm up so I can see what kind of progress that we're making. Okay, so the heart rate goes into that, and we can vary the distance. Now, hang on a second. Let's look at the body. And now what are you going to put next? What number represents that? Each number represents 1 and 2. Right? 1 and 2 goes into that. Right? You got it. Oh, no. Okay. No, it's going to be. Oh, see, it doesn't. You really need that. Otherwise, it's going to be true. Oh, I see. That's the only one. Oh, you need that. Oh, yeah. You know what it is? You opened it in Explorer. You opened it How you guys doing? On the Mac, just right click. Say save that. Save the desktop or whatever, and then say, save the. Yeah, you have to right click and say that. Yeah, okay, right click. Okay, now to the background. Now you can either open SPSS and say file open and look for it on the desktop. You can just do that one. Like this after How you guys doing? Oh, it's cool. That's 2 rows. That's excellent.
Yeah.
Okay. Well, first, we'll go everything we're going to hang on. That's the single one. Just do on 5. You want the
This one.
yeah. Yeah, that's the one, but you have to. No, I think we're in the. Got right click on it. Save. And save the desktop. And just save it. Now you find it on the desktop. The bill and other stuff. But good one. Hey, that's nice. No, you're still doing the same thing. You need to go on them, or you gotta make sure you have the right sample, the right file. You want the one that says heart rate, independent sample. So that's what we'll close that one. Okay, I go back to heart rate. Yeah, that's just one. Yes, I guess. And I go back. So, right when it was right? That was when we were doing simulation. Now move the heart rate, that's your numerical variable in there. And the grouping variable in there, that's the athletes and scholars. Now, let's go over the thing there. Tell it that 1 represents one group, 2 represents the other. Remember, because it's really coded, the thing is coded 1 represents athletes and 2 represents scholars. So put a 1 in there, and then put a 2 below. Okay, good. That's it, yeah, that doesn't have a code on it. Yeah, put in 1 and 2. Yeah. But that's really what's there. There you go. Yeah.
Wait, so is this the way it should be written out for the international?
Yes,
Absolutely. We gotta see what we got. Pick that, keep that. But we gotta comparing those numbers to what we get. Okay. So, you guys like afraid they go like sunburns? Only a little bit different. This says a little bit more. I'll talk about that.
Okay.
It might get a second. It's gonna be very strong. If you did it right, and I'm gonna compare it to the numbers I just. How are you doing?
There's more than two with the recording, one level
Okay, so, okay, guys, you know, unfortunately, the projector in this room sucks. So that's an epidemiology term. And so it's hard to see this. So I'm glad you have your monitors going here. Okay, so I'm going to do the same thing that you guys just did. Okay, now when I did it using Excel, what result did I get? I got a t-score of 1.96, and my t-critical was 2.28. So I failed to reject my null hypothesis. Let's see what happens when I do it using SPSS. I'm going to go to Analyze, as you guys did. It seems like everybody got this, eventually got to this point. Compare means. Now, this is not a single sample t-test because I got two samples, athletes and scholars, right? Two different X bars. I'm going to go down to independent samples, right? That means two groups, basically, two independent groups. I'm going to click on that. Comes up with a window that asks me, what variables am I using? So you could have a variable set has 50 variables in it. So you have to define what you're doing. So I'm going to move heart rate into test variable. Heart rate's a numerical variable. Move it into test variable lets SPSS know that we're going to find the means of those groups, the averages, right? That's the actual working average that we're looking for. But we want to break the result up into two groups, into athletes and scholars. So how does it know to do that? Well, we take the variable name sample and we move it into the grouping variable. Now SPSS knows that what we want to work with is we want to break it up into the two groups, athletes and scholars. Okay. However, the athletes and scholars are not really what's in SPSS. What's really in SPSS is the number 1 and 2. If I hide the value labels, it'll let me do this. See, it's really 1 and 2. The only reason it puts athletes and scholars there is because in the variable view, we defined 1 and 2 as represent athletes and scholars. So I'm going to go back to my calculation. So I got to tell it, look, it came up, it says sample question mark, define groups. Well, I'm defining the groups by telling it that group 1, athletes, is the number 1, and the group 2, scholars, is the number 2. So now it knows it won't read athletes and scholars. It'll read the 1 and 2, which is really what's there as far as it's concerned. So now I can say OK and have it do our calculation. Okay, let's see what our calculation looks like. I got two boxes. My first box, right, says it's basically descriptive statistics. Athletes, sample size is 6 and 6, 63, 70. Those are the same means we calculated, the same standard deviations we calculated. We didn't calculate standard errors for these because we knew we were going to have to pool them, right? So let's see what SPSS did for us here. Okay, well, first of all, the t-score is different than the t-score I calculated. I don't know why. I have to go back. Now I have to go back and check my math. Okay, but trust me, SPSS is right. Unless this, you know, I should check the files. Make sure the Excel file really matches the Excel file. So it calculated a t-score of 2.164, right? That's our t-score, right? So now, how many degrees of freedom? Well, just like we said, 12 minus 2 is 10, right? And what's the probability, the p-value, probability that we would get this extreme a difference between these two means if the null hypothesis were true? Another way basically of saying that we'd be wrong if we reject the null hypothesis. Well, we would be incorrect rejecting the null hypothesis 5.6% of the time. Is that enough? Can we reject the null hypothesis? No, because our significance, our p-value, is greater than alpha, greater than 5%. So we fail to reject the null hypothesis. Remember at the beginning we said we got to make a decision as to which formulas to use. We got to decide whether we have equal variances or unequal variances. And if you had equal variances, you would use this page. If you had unequal variances, you would use the formulas on this other page. Well, SPSS actually does the calculations both ways at the same time. If you look at the top row, that's the row for equal variances assumed. If you look at the bottom row, that's the row for equal variances. The other set of formulas, equal variances, not assumed. Not much of a difference. You can see a little bit of a difference in the p-value. There is a little difference, but not much, right? So how would we determine that? Well, the way that we determined it, informally, was to look at the standard deviations and see if one was double the other. And if it wasn't, we said that they were equal. SPSS actually provides a test for this. You see those first two white columns in the independent samples test? That's called Levine's test for quality of variances. It calculates an F statistic and a significance, a probability of being wrong if you reject the null hypothesis. What null hypothesis is it talking about? It's talking about the null hypothesis that the two variances are equal. And the alternative is that they're not equal, right? So which one of those two do you use? Well, you look at that significance in that second column and you say, if that's less than 0.05, I'm going to use the bottom row because I'm going to reject the idea that they're equal and not use the top row and use the bottom row instead. So that tells you use the top row, which is the same thing our original judgment was based on our loose, our informal interpretation was, right? So use the top row. So what's the t-score? It's negative 2.164, just 2.164, interested in the magnitude. And what's the significance? It's 0.056. Okay, again, 0.056 is not small enough a potential error for me to reject the null hypothesis because it's not below the threshold that I set of 5%. Okay. Let's take a quick look at that t-score. I'm going to go to the 10 degrees of freedom, the two N1, N2 added together minus 2, 10 degrees of freedom. I'm going to go to the t-table to see what critical value of t is for 10 degrees of freedom. Anybody want to hazard a guess? Is it bigger than 2.164, the critical value? The answer to that's going to be yes. Why is it going to be yes? Because we know that we didn't achieve a big enough t-score to reject the null hypothesis. So the critical value of t for 10 is going to be higher than that. Just to confirm that. Oh, got to move a lot of windows here to confirm that. I'm going to go, and we're going to take a break, and I'm going to go over my math while you guys are relaxing, having a cup of coffee, catching a nap. I'm going to go over my math and figure out why that didn't work. Why didn't we get the same number? T-score, T-table. Here we go. Okay, 10 degrees of freedom. The value of t that we would need to exceed is 2.228. That's our critical value. And you'll notice that in our calculation, the t that we got was only 2.164. It goes along. Exceed the critical value of t with your calculated value of t, you can reject the null hypothesis, which means that your significance is always going to be less than 5%. Your p-value is always going to be less than 5%. Okay? Take a break. Okay, it took us, we got started a little late. It always takes you guys a while to filter from the class you like into this class. I know that, right? Took you a little long. Took you a little long to get down here, but it took us an hour and a half to get to this point. So it's important that you understand this because we have so much time invested in this. Okay? So we've learned how to do a single sample t-test using Excel and SPSS. You're mostly going to, in real life, use SPSS. And we learned how to do a independent samples t-test in Excel and SPSS. And I'll calculate why we got that. And take a break. Get up, walk around while I do the calculation again. Yes. Yes.
Professor De Vito. Hello. Professor De Vito. Can I ask you a question?
We do it on both. They're both always going to be the same. In other words, if your T calculated is bigger than T critical, alpha, the p-value is always going to be less than 5%. They're always going to go together. You're never going to get a case where you exceed the critical value of T with your calculation, and the p-value is more than 0.05. Okay, so those two numbers will always go together, hand in hand. Okay, so let me do this calculation again. Yes. Oh, good. Thank you very much. How could I get this wrong? I don't understand. P critical.
Hello, Professor De Vito. Can I ask you a question,
Okay.
please?
So this is, let's see, what do I got there? A2 through A7, okay. A8 through A13. Let me check the numbers first before I do anything else. Oh, I see Mariana.
Yes, yes.
Hang
Professor.
on, Mariana, I'll get to you in a second.
Yes, thank you. Thank you.
Okay. Let me get to the data window and make sure these numbers are the same. Okay, where's Excel? Okay. 65, 65, 70, 65, 55, 60, 78, 79, 70, 79. There we go. The numbers are the same. Okay, so I'm going to do this from scratch. Okay. Continue. Which? Yep, and 8228. Up. I think I found my mistake. Yep, I found my mistake. That didn't take long. There we go. Okay. Now, it didn't take me long to find a mistake there. Literally, the first thing I did was where I made the mistake. When I calculated the average over here, I put in, I'm going to undo. It was originally A6, A6. It's really A7 athletes. So I only counted the first 5 athletes, not the all 6. So I need to change that to A7. Right? This mean equals average. Did you guys got a different number than I did? Hang on a second. I'm going to get all the athletes. I got 63. So go in there and check carefully to make sure that when you took the average, you only took the average of the 6 athletes. I got a feeling that you took the 7th guy too. Let's see what happens if I go too far.
Oh.
Yeah, that's what happened. Yep. See what happened. Yeah. So. Yeah, and look what happened. I'm going to go all the way down here. The nice thing about Excel is that if you go back over your calculations and you build from one to another, when you go back and find an error, if you correct that error, it goes through all the calculations and corrects them. And our t-score is 2.16, which is the same thing that we got in SPSS. So we got that right. Okay. So Mariana, are you here, Mariana? Or are you away somewhere?
Yes, Professor. Yes, Professor David, I'm here. Can you hear me? Hello?
I can't tell, when you're logged on, I can't tell if you're in the room or if you're, yes. I'm sorry, say it again.
Next week,
yes.
Our morning nutrition class is offered online.
Yes.
So we're not coming to school. Is it okay again if we attend online?
Yeah, I think it'll be okay.
Okay. Thank you.
What's with this nutrition class?
I know. Second time.
Okay.
Maybe because Thanksgiving week.
Yeah, that's probably, that makes sense. Okay, yeah. Now we're going to start doing something different next week. So we're going to kind of change gears a little bit next week. It's going to be a different kind of test, but that's okay. When we come back the following week, I think we got an exam the following week after Thanksgiving, right?
Are you going to do another review?
What's that?
Before the exam?
Yes, I'll do another review. And I'm not sure whether what I do next week is going to be on the exam. As a matter of fact, I think it will be, but it'll be a relatively small portion of the exam. What we covered next week. They will be on the exam, but it's going to be a relatively small portion.
Hello, Professor De Vito. Can I talk to you, please? This is Mariana. Can you hear me? Professor De Vito, can you hear me?
Sure. Hey guys, make sure you sign the attendance sheet, please. So I can make sure you get credit for showing up.
Do we have to email you to remind you that you're going to be online?
No, that might be a good idea. Yeah. I'll put an announcement on Blackboard and I'll send it out as well.
Professor De Vito, can you hear me?
This conference will now be recorded.
Okay. Yeah, I paused while we took that break. Okay, so just to reiterate for the people that might be listening to this later on, turned out that the error that I made was when I first started, I put in for the average for the athletes A2 through A6. So I calculated an incorrect mean for X, right, for X bar A. And that got carried through all of these calculations. This actually, I don't think this is E2 minus E3. E2 minus E3. That got carried through all these calculations. Before it was 63. And so on and so forth, got carried through all these calculations, and we wound up with a t-score of minus 1.96. When I went back now and corrected that, because the athletes go from A2 through cell A7, when I corrected that, well, now we wound up with the correct t-score of negative 2.16. Okay, so, and we find that, in fact, if I go back to SPSS, that indeed is the t-score that SPSS calculated also, negative 2.164. Okie doke. And since that doesn't exceed our critical value of t for 10 degrees of freedom, then we find that the significance is bigger than 0.05. That p-value or significance, probability of being wrong, is greater than 0.05. So both of those go hand in hand, tells we reject the null hypothesis. And as you just pointed out, when t-critical and t-calculated are exactly the same, the p-value is 5%. Probability of being wrong, if you exactly match your t-calculated exactly matches the t-critical for that number of degrees of freedom, that means there's 5% chance of being wrong. As your t-calculated goes above t-critical, meaning that the two means are further apart than you need, then your significance or your p-value goes below 0.05. Reject the null hypothesis. If your t-score, if your difference between your two means is smaller, your t-calculated comes out to be less than t-critical. That means they're too close together, and your p-value becomes greater than 0.05, and you fail to reject the null hypothesis. So I think if you work with this a little bit more, you'll work it out. Okay, so now what's the next possible scenario that we might have here? And that is a situation where you do a study, and let's say we take athletes and scholars. Maybe one of the reasons why athletes have a lower heart rate is because they exercise more, they eat better, so on and so forth. Maybe it's because the scholars have more smokers than the athletes do. Maybe there is some confounding variable in there that we don't see, and it turns out that 3 of the scholars are smokers and none of the athletes are smokers, right? So it confuses the issue. Maybe the scholars are older than the athletes are. Maybe the athletes only have a certain amount of eligibility, so that they're only in school for a limited amount of time, and the scholars, maybe some of them hang around longer, right? So there could be a lot of things. Could be age differences, right? So, a lot of times when we do studies like this, when we just want to say test the effect of a drug, we can do it two ways. We could take 100 people and give them a placebo. Let's say it's a blood pressure medication. We could take 100 people, give them a placebo, and see if their blood pressure goes up or down. We could take another 100 people, give them the drug, and find out whether their blood pressure goes up or down, right? So now what do we wind up with? We wind up with two means that we can compare. That's an independent samples t-test. One group of people takes the placebo, the other group of people takes the drug. Well, maybe this group B, maybe it had a lot of people that were diabetics. Maybe there was something buried in there we didn't catch in terms of medical history, the health of the people taking the drug might have made the other group, the placebo group, that we didn't catch that confounds our results. Well, you know what we can do instead? Let's just take a single group of 100 people, and for 2 weeks, they take the placebo. Some of them take the placebo, 50 of them take the placebo, 50 of them take the drug. And we measure their blood pressure after 2 weeks. Then we switch it around. The people that were taking the placebo now take the drug. And people who are taking the placebo now take the drug, now take the placebo, and we measure their blood pressure in 2 weeks. Well, now we have 100 people, and we have their blood pressure before and when they took the placebo, and their blood pressure when they took the drug. And we can calculate the difference between their blood pressure on the drug and on the placebo. But each difference is for the same individual. So we don't have to worry about whether we're comparing a person that smoked a lot or was older or diabetic to a person that wasn't, right? Instead, we're comparing everybody to themselves in terms of their response. That's called a paired sample. The readings are done on the same subject twice under two different conditions. So, are we interested in what their starting blood pressure was? No. We're interested in if the drug or placebo changed their blood pressure. So, placebos can work sometimes too. That's why we want to test placebo. So, we're not really interested in what the average blood pressure was, when they were taking the placebo, what it was when they were taking the drug. We're more interested in what the difference was for each person. So now I'm going to open up that file. I don't know if I have it in Excel. Let's see if I do have it in Excel on Blackboard. Heart rate, paired sample for fluoride. Yeah, I'm gonna open this up in SPSS. I'm gonna open this up in SPSS. Okay, so here is a fluoride paired sample test. Maybe I don't know what maybe this testing. Maybe this is tooth enamel, hardness of tooth enamel, right? I'm making something up here. Hardness of tooth enamel, and we're giving them a fluoride treatment. Before the fluoride treatment, this was the hardness level of each person. Person one, before hardness level of their enamel was 12. After, it was 49. Before 5.2, after 16. Let's see, this one before 21, and then it went down afterwards for some reason, right? So we're looking at, for this each person, the difference between before taking the fluoride and after taking the fluoride. It's not one group didn't get fluoride and the other group did get fluoride. It's the same person. So what we're really interested in is the difference between these two. I'm going to take these numbers and I'm going to put them into Excel. I'm just going to go over here and I'm going to say, you're going to see, I'm going to just say, highlight them. I'm going to say copy. I'm going to open Excel. It's going to save you the trouble of going back. If you open it, it's up, and download and open this file in SPSS. It'll save you the trouble of having to download this or find it. Okay, and I'm going to say paste here. There are numbers. There's one group before, one group after. Right. Am I really interested in the averages of these two columns? No, I'm interested in the difference between the two. Equals this value minus this value. Okay, that's 31. Difference is 31. If I copy this down, I'll get all 16 differences, right? So if there's no difference between taking the fluoride treatment and not taking the fluoride treatment, what would you expect the average difference to be? If the fluoride treatment doesn't do anything, you would say on average the person's teeth won't change. It won't be any harder or softer than when they got the fluoride treatment, right? If the fluoride treatment doesn't work, so the average is going to be 0. That's our expectation, right? Is that the average is going to be 0. So I'm going to open up a sheet of paper, and I'm going to write a null and alternative hypothesis. Okay, except this time, remember, I'm not interested in what the person's hardness was when they took it, when they didn't take it. I'm interested in the difference, the mean difference. Right? Okay. So my null hypothesis. What's my null hypothesis here? My null hypothesis is that the drug didn't do anything. The mean difference is equal to 0. My alternative hypothesis, the mean difference is not equal to 0. The drug did something. It changed the hardness of the person's teeth. Maybe it softened them, maybe it hardened them, but it made some sort of change. So I've defined my null hypothesis this way. Okay, and then I'm going to go here and tell you what my alpha is going to be. As almost always, say it's equal to 0.05. Okay, so now I want to go ahead and do my test. How many samples do I have here? Is this an independent sample test or a paired sample? Is this independent or single sample? How many samples am I looking at? How many columns of number am I going to analyze? I'm not interested in the before and after. I'm only interested in the difference. The difference is only a single column. I'm going to compare my average difference to the value 0. That's what a paired sample test really winds up just being, a single sample test using the value 0 for the null hypothesis. Guys get it? In other words, we want to see if there's a difference or isn't a difference. So I went to Excel. Let me go back to Excel if I can ever find it again. Let me try this one. I went to Excel and I said, okay, let's see. I said, okay, the difference between these two groups is in this third column. And I'll calculate the difference right here. And the difference is an average of 12, right? Is that big enough difference from 0 for me to reject my null hypothesis? Well, I got to do the calculation. Remember, this is a single sample t-test now, right? So in other words, t is going to be equal to x bar minus mu that I'm comparing it to, the average I'm comparing it to, which in this case is 0, divided by the standard error. Okay, good. Okay, so let's calculate what these are. Okay, first of all, the top part of this, x bar minus 0, is just x bar. That's the top part of that equation. Well, what's the standard error equal to? Okay, let's calculate our standard error. Okay, what's our standard error equal to? It's equal to, I need the standard deviation. The standard deviation over the square root of n, right? So I need to also calculate not just my average, but I got to calculate my standard deviation. Okay, standard deviation of this column of numbers, okay, which is 13.6. So let's see, standard error is equal to, let's see, standard error is going to be equal to 13.6, our standard deviation, divided by the square root of the sample size. What's the sample size? What's the sample size? 16, right? Okay, so square root of 16 is 4, so I'll just put 4 there. Comes out to 3.04. Okay, and now let's calculate what our t-value is. Our t-value is equal to x bar minus 0, which is this 12.215, divided by my standard error, which is equal to, is that right? Yeah, 3.4, which I just calculated. So my t calculated is equal to 3.58. Now, does it exceed my t critical? Sure looks like it, but we're going to check it, right? So let's go over here, go to my table. Oops, what did it do? Go to my table. And for how many degrees of freedom? Sample size is 16, single sample test, 15. I'm going to go over here, and we need to exceed 2.131. So my t critical is 2.131. Do I exceed my t critical? Does my t calculated is bigger than my t critical? Yes. So what do I do with my null hypothesis? I reject my null hypothesis, and I accept my alternative hypothesis. Okay, everybody comfortable with that? Now you guys do the same thing using SPSS. And how are you going to do it? You're going to use analyze, compare means, paired samples. Now you're going to have to download this file. You're going to have to download the file, the original file, which was called, what was it called again? Which was called fluoride paired samples.sav. You need to download that to your desktop and give it a try. Okay, and if you got it downloaded, open in SPSS. And you're going to avoid having to do all these various calculations. You're not going to have to calculate the differences or the mean difference. If you wanted to, actually, there is just as you're working, I'm going to point out that there is a way to do calculations on variables in SPSS. So, for instance, I can go up here to the top where it says transform. Okay, work on what you're doing as I'm talking here. Go to transform, and I can say to recode into the same variable, recode into different variables. In this case, it's going to be computer variable. So I'm going to create a new variable. I'm going to call that variable difference. And I'm going to say that the difference is equal to the after value minus the before value. The variable after minus the variable before for each individual. And then I'm going to tell SPSS to go ahead and create that function, that variable. I'll click OK. Okay, and notice the output table comes up just to tell me what it's done. Notice it created a new column with all the differences, just like Excel. Okay, those are the differences. You don't really need to do that to do the t-test, but in case you're curious about it. Okay, so I'm going to give you guys give me a little heads up. Thank you guys. Oh, you already did it. Oh, yeah. I can't see it. I'm blind. I say it's below. I didn't mean to like take a check. Oh, okay. Yeah, you should get, this program is like $1,000 program that,
Oh, yes, you calculated, you do the transformation. Yeah, I like. Okay. Perfect. Did you do that or did you do that? Okay, good. Don't tell me how to. Okay, now the thing here is that there are two variables that you start with, before and after. So when you do a paired sample because you want to know the value of before and after. Like I just showed I can calculate the differences when I wanted to, but you didn't need to do that. So you just move before and after into that right side. He's waiting for two. Oh yes, it doesn't matter. Yes, he's waiting for 1 minute and 30 seconds. That's it. That's it. All right, then. All right, compare that to actually calculating it in Excel. Okay, guys, I'm going to go ahead and do this up front here, and we'll see if we get the same answer. So I'm going to go to Analyze. I'm going to go to Compare Means. I'm going to go to Paired Sample T-Test, because that's what this is. And it comes up with a window where it's asking me to tell it what variables to work with. Which are the paired samples? And the paired samples are variable 1 and 2, which are after and before. It doesn't matter which one you put first. And it won't let you do anything until you've put 2 variables in there. So you can calculate the differences. I'm going to click OK. And bingo, pulls up the output window. And our output window has our paired sample t-test. So let's take a look at what it did for us. Okay, first, paired sample statistics. The mean before and after, mean before was 38, mean after was 26. That's really irrelevant to us, right? Because we're not even really interested in that. It's really the differences we're interested in. So if I go down here to the paired sample t-test, the mean that it gives us is the average difference, the average before and after readings, right? Which is 12.21, same as we calculated. And the standard deviation is 13.6, the same as the standard deviation of all the differences was 13.6, as we did in Excel. So the standard error is equal to the standard deviation divided by the square root of the sample size. Sample size was 16. Notice it says 15 degrees of freedom there, 16. So that's 4. So that's 13.61 divided by 4 gives us 3.4 standard error. So it's going to take the mean, divided by the mean difference, divided by the mean difference. Remember, we're comparing it to 0. So it's 12.621 minus 0. X bar 1 minus mu, where mu is 0, right? 12.21 divided by the standard error is 3.4. So it's going to give us a t-score of a little under 4. So I'm going to go across here and go across here. Don't worry about confidence interval right now. Here's our t-test. Just as we did in Excel, it found that the t-score, number of standard errors apart, 12.2 and 0 is 3.6 standard errors apart. That's a lot, right? If I looked up the critical value, it came out to be 2.1 or something like that. So we have well exceeded the critical value that we need to reject the null hypothesis. Not only that, but I know since this has exceeded the critical value, I know without even looking, I'm going to cover it up, without even looking, my p-value is going to be less than 0.05. And if I pull this away and look, indeed it is, it's 0.003. And it's so small because the t is so large, right? Unusual to get that big a difference between the 0 and the difference that we have actually calculated by chance, right? And it's very unlikely to do that. Degrees of freedom happen to be 15. So really, you really could ignore the t-test if you wanted to in rejecting the null hypothesis. You could just look at the p-value and see if it's less than 0.05, right? Or you could just look at the t-test and say, oh, I can reject the null hypothesis, I'm done. The advantage of looking at the p-value, that 0.003, is it not only tells you whether to reject or fail to reject the null hypothesis, it also gives you an idea of how certainly what level of confidence that you have in your result. So now you can say, gee, not only is there less than 5% chance of being wrong if I reject the null hypothesis, but really there's less than 1% chance of being wrong. So I really feel confident with this result. right? So that's the advantage of having that p-value, is that you get a better window of where you are with this calculation. Okay, and that's really it. Now, the other thing that might come up on occasion is proportions. Okay, I'm going to go back to that page, that written page. Okay, you guys all have this. Okay, the last thing on this written page is, okay, two populations. Okay, the last thing on here is comparing two population proportions using hypothesis testing. Well, boy, this is really messy stuff. I'm just going to go through this page, and then I'm going to do an example in which we're only dealing with a single sample for a proportion. Because I don't think on an exam I would ask you to do this necessarily. Okay, so let's look at this. What does this tell us? Let's say we have two proportions. We're dealing with two population proportions. Okay, well, when we're dealing with proportions, we're only going to deal with large samples. The real rule is that the general rule is that sample size has to be greater than 30. With each group has to have at least 15. So, like in other words, if you're talking about diabetics and you sample 100 people and 10 of them diabetics, 90 of them aren't, that doesn't meet this criteria, right? Because you got one group that's less than 15 in. So typically when you're dealing with proportions, that's binary information, right? Yes or no. I'm going to vote for Hillary. I'm not going to vote for Hillary. He has diabetes, doesn't have diabetes. That's binary information, right? Proportion, right? Horse wins, horse loses, right? Horse doesn't win. So we're usually dealing with large sample in that case, because you don't need an elaborate survey, 20 minutes to get that information. Usually it's pretty quick, right? So how do we handle proportions? Like for instance, let's say I want to know whether the percentage of diabetics in one population is different than the percentage of diabetics in another population. Well, what's your null hypothesis going to be? Your null hypothesis is going to be the p-value, percentage of diabetics in population 1 is equal to percentage of diabetics in population 2. What's your alternative hypothesis? P1, proportion for population 1, is not equal to the proportion for population 2. Okay, so now you actually go ahead and do a sample, right? So let's say you sample 1,000 people from population 1 and 1,000 people from population 2. And it turns out of the 1,000 for population 1, 150 of them are diabetic. So what's your proportion? What's your p-value? It's 0.15. 150 out of 1,000, 0.15. And for the other group, P2, it's 200 out of 1,000. That's 0.20. Is that P1 and P2 really? No, it's not. It's not the entire population. It's only your sample of 1,000 people, right? So we call it P anymore. When we're talking about the sample proportion, we call that P cap. So it would be P cap 1 is equal to 15%. P cap 2 is equal to 20%. Well, given those sample sizes, you have enough information to reject the null hypothesis. In order to do that, we have to do a t-test, right? The sample size is so big, 1,000. Sample size is so big, we don't bother with the t-table. We just use the lowest t-value you can have, which is the z-score. We just use 1.96 for 5%. So we just need to prove that the difference is big enough to have a t-score or a z-score that's bigger than 1.96, because of big sample sizes. Okay, so we're going to pick alpha is equal to 0.05. That's why we use 1.96. If we wanted alpha to be 99%, we would pick 2.58. Remember our confidence interval? 2.58 for 99%. Okay, so calculate the z-value. The calculated z-value, you can call it t if you want. We're going to compare it to t. It's going to be p cap minus p cap 1 minus p cap 2 over the standard error. Okay, actually it should be p cap 2. I have this as a PDF. I got corrected somewhere else. Okay, over the standard error. Right. I'm sorry. This is if it's a single sample. We're comparing it to known value. This is what we would use. We would say p cap minus the known value. I'll work on that in a second. The standard error is going to be the square root of. We've seen this formula before. when we did the confidence interval for proportions, the square root of p cap times 1 minus p cap over n, square root of that whole thing. As our standard error, and we just take p cap minus the known value divided by the standard error, which is this number, and that would give us a z-score. And if that z-score is greater than 1.96, we'd reject the null hypothesis. Well, this page is really comparing the proportions for two samples, right? P cap 1 is equal to p cap 2, or it's not, right? Well, in that case, it gets complicated, okay? And the z value is equal to, it's equal to a pooled p cap, right? P cap, put a cap on it, pooled p cap, is equal to p cap 1 times n1 plus p cap 2 times n2 over n1 plus n2. And then once you found that p cap, that pooled p cap, then you use the formula down here, p cap 1 minus p cap 2 over the square root of the pooled p cap times 1 minus the pooled p cap times 1 over the sample size, 1 over sample size, like 1 over 1,000, 1 over 1,000, added together. So would I ask you to do this on an exam? I'm not a masochist. I would not ask you to do this on an exam, right? So the worst you'll ever find on an exam is a single sample situation where I ask you to analyze a proportion. And that's really only the same thing as calculating confidence interval, basically. So I'm gonna, you might wind up with something like this. And open up a new Excel file. Okay, so the way I might, conceivably phrase this is, let's say that you sample, your sample size is 1,000. You sample 1,000 people, and you ask them, what's current now? Let's see. You ask them whether or not they believe that we're going to put a proposition in place in California where we're going to budget over the next 5 years $1 billion additional money for forestry control, or management of the forest. But the problem is that $1 billion coming out of the education fund. So we're going to cut the education fund by $1 billion, and we're going to put it into maintaining the forest. And we're going to put this forward as a proposition in a special election in 2 months. And now we want to analyze whether or not the majority of people will vote yes for this proposition. Put money into $1 billion in the forest, but take it out of education. We want to know. So what is our threshold here? Our threshold here is 50%, right? In other words, we want to know whether 50% of the people are going to vote for this proposition, right? So we're going to take a sample of 1,000 people. And the number of people that, out of those 1,000 people, the number of people that vote yes turns out to be 540. Number of people that vote no turns out to be 660. I'm sorry, 460. Right? So what is our p-value here? What is our p-cap here for this sample? P-cap is equal to 540 out of 1,000. Right? In other words, 54% of the people are in favor of this proposition in our sample of 1,000 people. Hang on a second. Now, before we go forward here, I'm in favor of this proposition. I've got to figure out, do we want to spend money on like advertising and encouraging people to vote yes and so on and so forth? How sure can I be that the rest of the population really is above 50%, right? What we're going to do is we're going to compare our p-cap to 50%, right? So how am I going to do that? Well, first of all, I know p-cap is 50%, and I know that the p that we know, p known, is 50%. I'm sorry, let me rephrase that because I think I said that twice. The p that we're comparing it to is 50%. That's a known value that we want to know whether we exceed or not. And p-cap is what we got from our sample. So what do we want to know? We want to know, is that big enough a difference to say with 95% certainty that we're really dealing with something that's going to pass, right? Okay, so let's find out what, and how are we going to prove that? Our null hypothesis was Well, null hypothesis is p cap is equal to 50%, and our alternative hypothesis p cap is not equal to 50%. In other words, in our case, we're interested in it being more than 50%, right? Not equal to 50%. So how are we going to test that? Well, we're going to do a z-test or a t. We could call it a t-test, except we're not going to use the t-table. We're just going to use the values on the normal distribution. So I'm going to call that z-calculated, just like I would have called it t-calculated. In fact, I could still call it t if I wanted to. Z-calculated. Okay, so what is z-calculated going to be equal to? It's going to be equal to p cap minus p known over standard error. Okay. Let me put a few dots in there so that it knows that to go away. So let's calculate that. So the top part of this equation is going to be 0.54 minus 0.5. It's going to be 0.04. That's the difference between the two. The bottom part is going to be the standard error. And how do I calculate standard error again? The standard error is equal to the square root of p cap, which is 0.54, times 1 minus p cap, which is 0.46, right? Divided by, actually I can just do divided by the sample size, which was 1,000, right? Those are all multiplying divide, so I don't have to separate them, I don't think. So what does that come out to be? The square root of 0.54 times 0.56 over 1,000, square root of p cap times 1 minus p over n, turns out to be 0.01576. Okay, so what's our t-score? It's equal to our z-score, rather. Z, or t, is equal to, it's equal to 0.04, I'll put it in here, is equal to 0.04, the difference between the two proportions, divided by the standard error. And it comes out to be 2.53. That's how it's calculated. Okay, what was our z-critical? Remember, it's a gigantic sample size. The 5%, what's our z-critical? 1.96, right? Have I exceeded my critical value of t? Yes. So can I reject the null hypothesis that the majority of population, or at least our result, is different than 0.05, in fact, larger, right? So I can be less than 5% chance that this proposition is going to lose. In other words, less than 50% of the people are going to vote for this proposition. Right? So that's a single test, except using proportion. You're doing the same thing. You're looking at the difference between two proportions, a calculated one based on a sample, and so on and so forth. You know, another way I could have done this, I could have said, what's a 95% confidence interval? For the true, based on this result, that p cap is equal to 0.54, what's a 95% confidence interval for the true proportion of people that are going to vote yes? Well, it's going to be equal to p cap, which is 0.54, plus or minus. Right, let me get this in front of this so I can. Plus or minus the 1.96 times the standard error. Okay, let me go ahead and calculate that. It's going to be equal to 0.54 minus, I'm only going to do minus because the other one's going to be higher, right? Minus 1.96 times the standard error. We calculate standard error the same way, it doesn't matter. So I'm just going to put that in there. Okay, and it's going to do that first, and then it's going to go, okay, that'll work. And what is our lower limit of our confidence interval? It's 51%. So we're 95% sure that the true proportion of people who are going to vote yes is between 51% and 3 below, it's going to be 57%. So what does that tell you? You're 95% sure that it's going to be above 50%, right? Because 50%, it's not in here. You're 95% sure the true population proportion is going to vote yes. is between 51 and 57, that also means you're 95% sure it's not going to fail. It's not going to be below 50% because 50% is outside of the confidence interval. You can use the confidence interval to determine whether or not the value that you're comparing it to is within or outside of the confidence interval for a single-sided test. You can't do it for a single sample test. You cannot do it for paired sample, for independent samples test. Equal variances, unequal variances for two proportions and so on and so forth. There are mathematical reasons why you can't do it, but you can do it for single sample tests. Okay, so that's as complicated as I think you would get.